and this whole chapter is all on solutions. So we first start in the first section talking about what is a solution. And it's not a new concept because we learned about this already. When we talked about types of substances, we talked about pure element, pure compound, and mixtures, right? Within the mixtures, we have homogeneous mixture and heterogeneous mixture. So a solution is basically a homogeneous mixture. And remember what homogeneous mixtures means? They are well mixed together. You can't tell one part from another part if the concentrations of the parts are equal throughout. Okay, so that's what a homogeneous mixture is. And so when we talk about solution, it is a homogeneous mixture. And a little bit more vocabulary here, a mixture is composed of two things. One is called the solvent and the other one is called the solute. And the difference between these two is the amount you have of them. So whatever that is in larger amount is called the solvent. Whatever is in smaller amount is called the solute. So for example, if you take a cup of water and you take some salt and you dissolve that salt in that water to make a saline solution, what is a more abundant substance there? That's the water. So the water is the solvent, and the salt, NaCl, that you add into that water is called the solute. The solute and the solvent together makes up the solution. Now there are different phases for a solution. They can exist on all three phases. They can be a gas phase, liquid phase, or solid phase. So for example, the gas solution, one prime example is air. Air is a mixture of different molecules. And the most prominent component of air is actually nitrogen, not oxygen. So we would say that air is a solution, a gas solution, that contains oxygen as the solute and nitrogen gas as the solvent. And we can also have a solution in solid form. For example, steel. Steel is solid. It's actually composed mainly of iron. So iron will be your solvent, and then sprinkled throughout that iron are carbon. So carbon would be your solute. Okay? Now, gas solutions and solid solutions, they're good to know that they exist, but in reality, the solutions that we really care about are liquid solutions. What is liquid solution? It's a solution in the liquid phase. Right? So some examples here you may experience with in your everyday life. The first one is household ammonia. So household ammonia is actually a solution, a mixture of ammonia gas in liquid water. So again, which one would be the solvent? Water is your solvent and ammonia is your solute. Our next example here is vinegar. Vinegar is actually composed of acetic acid and water. A small amount of acetic acid in a large amount of water. So acetic acid is your solute, water is your solvent. And finally here, our last example is that saline. Saline or seawater is basically NaCl, sodium chloride, dissolved in water. So again, sodium chloride will be your solute and water will be your solvent. So now the difference between these three examples is the phase that the solute is in. For example, ammonia is a gas in a liquid. Acetic acid is a liquid in a liquid. Sodium chloride is a solid in a liquid. So you can have three phases, gas, liquid, solid, both dissolved in water. The second thing I want to point out here is that notice that water is a solvent for all of these things. It turns out water has a special ability. It's called the universal solvent. And let's think about why water would be a universal solvent. So to be a good solvent, you must be able to interact with your solute. Now what gives water the ability to interact with the solute? Now this comes back to our previous chapter on looking at the structure of water. If you draw in the Lewis structure for water, we have oxygen connected to two hydrogens. Remember the geometry of this is that it is a bent molecule. Because of those lone pair, it makes it a bent molecule. And what is the polarity of this compound? Oxygen is more electronegative, so it pulls electrons this way. Oxygen, again, is more electronegative than hydrogen, so it pulls electrons this way. So that if you add these two dipoles together, the overall dipole moment of this molecule, that the electron density is high, on the top near oxygen and low in the bottom near hydrogens. Like we can say that that the oxygen side is your partially negative and the hydrogen side is your partially positive. So how does this help it interact with things? Okay. So now let's think of one example. The most obvious one is sodium chloride. Right. So if you have sodium chloride, sodium is what charge? Positive 1. Chloride is negative 1. So this is a cation, so it's positively charged. This is an anion, so it's negatively charged. Together they are a solid, so because they like each other so much, they cling on to each other, so they are a solid. Now as soon as you put this into the water, if water cannot separate them, they will remain a solid, separate from the water. But, however, water has a special ability to separate these two. Coming back to our idea that water is negative on top, near the oxygen, and positive near the hydrogen. What do you think, which side of the water will try to interact with this positively charged sodium? Opposite attracts, right? Negative, positive, they will attract each other. So this water will come in and present its negative face, which is oxygen, and not hydrogen. This is its negative face towards, right? So this is partially negative, towards the sodium. Okay, so this interacts with the sodium, so I'll draw in the interaction. So I'll highlight the interaction here. This negative with this positive. Okay, so you got one water molecule, negative side, trying to lure away the sodium, the positive ion, towards itself. But that's not strong enough, right? This is just a partial negative. How can I compete with a full-on negative charge? So the second thing about water that gives it its ability to be a universal solvent, not only because it has a negative charge and a positive charge within its molecule, but is the fact it is very small. So what does being small have to do with anything? Well, it turns out that if you have one water molecule trying to attract sodium, it can't do it on its own, right? So it starts to recruit other molecules, other water molecules. Because water is small enough, it can fit into right here to start to, again, interact with this cation and try to attract it. You can add more, right? So,
again, because they're small, they will try to interact. You can have it up here. Right?
So there's a lot of attraction now, so much they gang up on this sodium guy so that it pulls and attracts it away from the chlorine. Now, again, that's on the sodium side. What about on the chlorine side? You notice, remember, that water has a positive side too, right? So that positive side would now try to attract this chlorine, which is a negative. So instead of presenting its oxygen face towards this compound, water now will present its partially positive end. Positive, positive, right? So you can imagine then, this chlorine is negative. Ooh, sees positive charge. Okay, fine. I'll bond with you. Again, water is a small enough molecule that you can see this happening many, many times over. And because of this, eventually sodium and chloride will separate, and then water now surrounds all of sodium with its oxygen facing it, and chloride is surrounded by water with its hydrogen facing it. Because of this, sodium chloride is no longer solid, it dissociates and then disappears into the water. Okay, so that's how water can dissolve an ionic compound. Let's now imagine how water can dissolve not ionic compound, but just a polar molecule. Remember, we can represent a polar molecule because it's polar. One side is negative, one side is positive. So to make it easier, I'm just going to draw in a symbol that says positive side and negative side. And remember that water is also a polar molecule. So water can also be represented as a positive and a negative. Remember, this negative was the oxygen side, and this positive was the hydrogen side. But I'm just going to represent it generally with a block with positive and negative ends. So if you have if you have a polar molecule, and this polar molecule again may be attracted to each other, so the polar molecules attract to each other, so it's positive attracted to its negative. Because of that, that solute likes to be together, either as a liquid or even as a solid. That polar molecule will be stuck together, right? So how does water then come in to disrupt that interaction in the same way as the ionic situation? Because water has a positive end, that positive end can come in and face it towards this negative. Towards that. Positive towards the negative again. Alright, and then this other end, remember that water has two ends to it, so it can turn around and have that positive interact with this negative end now. Okay? In the same way, this guy now doesn't have to be with with another molecule just like it, but it can interact with water, and so it separates from its own molecule and be surrounded by water instead, and is still happy because of these interactions. Alright, so now lastly, we just talked about how water can dissolve ionic solutes, and how water can dissolve polar molecules also. Now, it turns out water can't dissolve one other thing. Now, let's see why. If you have a molecule that is non-polar, for example, if you just have a molecule that looks like this, let's say I give you this molecule and ask, will this be dissolved by water? What would you say? What do you notice about this molecule? Even though it looks complicated right now, it's not quite complicated. What kind of bonds does it have? It has carbon-carbon bond and carbon-hydrogen bonds. What do we know about the polarity of those bonds? Carbon-carbon, so it's going to be a non-polar bond. Carbon-hydrogen, remember carbon-hydrogen have the same electronegativity of 0.4 difference, so it's also going to be non-polar. So this entire molecule is non-polar, right? So if it's non-polar, can a polar molecule interact with it? Remember, the polar molecule of water is a magnet. If this magnet wants to interact with this has to be some positive and some negative sides, right? But this doesn't have any real permanent negative or positive sides. Because of that, water, rather than interacting with this molecule, just wants to interact with itself. Right? Water can just interact with itself. Its positive end can interact with its negative end, and so on and so forth. Okay? So because of that, these two cannot dissolve into each other. Okay? So, for example, this is hexane, which is an oil, and this is water. So if you add water and oil together and you mix them, eventually what do you see? They start to separate, because they rather exist as two different layers. As the water layer, because it has good interaction with each other, rather than mixing the water with the oil, because the oil has nothing for the water to interact with. Okay, so it's all about the intermolecular interactions, whether something will be solvated or not. So we just saw that water can dissolve ionic compounds, water can dissolve polar molecules, but water cannot dissolve non-polar molecules. So let's see if we can apply this concept into a situation in the lab. So in the lab, let's say we have a mixture of water and this compound called carbon tetrachloride. Okay? What do we know about water again? Water was a polar molecule, right? Because it's bent. We just talked about that. What about CCl4? Will this be a polar or non-polar molecule? How would you know that? So we have to go back into our previous chapter and know the shape of this molecule. And the shape of this molecule would be tetrahedral. Because of the very good geometry on this, even though this is a polar bond, this is a polar bond, and these two are polar bonds, they pull equal strength away from the center, canceling each other out. So this is actually a non-polar molecule. Okay, so what happens when you, in the first test tube here, if I added the polar water and the non-polar CCl4, what would happen? Would they mix well, or would they separate into two layers? Right, just like water and oil can't mix well and they will separate into two layers when you make your salad dressing, in the same way, they will separate into two layers. One layer will be on the bottom and one layer will be on top. Whichever is a more dense layer will be on the bottom. And it depends on the density, right? So in this case, we just, I will tell you that it will separate into two layers, and the top layer, which is a less dense layer, is actually water. And the bottom layer will be CCl4. So they separate into two layers. Okay, so I do that for 3 test tubes. So all 3 will have water on the top and CCl4 on the bottom. Now here's the test. In the second test tube now, I add a third species, I2. The question then is, where will I2 dissolve into? Will I2 dissolve in the water layer, or will I2 dissolve in the CCl4 layer? What do you think? How do you determine this? Okay, so let's think about the polarity of I2. If you draw out the Lewis structure for I2, go ahead and draw that out. Try it on your own first. I2 will have a Lewis structure like this. Right? Is this a polar bond or a non-polar bond? They're identical to each other, the atoms, right? So that's going to be a non-polar bond. So if this is a non-polar bond and there's only 2 atoms involved here, will this molecule be polar or non-polar? It will be non-polar. Okay, so if this molecule is non-polar, would water want to interact with it? Water is happier interacting with itself than interacting with something that doesn't have a charge, right? So it turns out that water will not dissolve it. So instead, it turns out the iodine will go then down into the other layer. And because they're both iodine and CCl4 are both nonpolars, they are okay to mix because they don't lose anything when they mix. Okay, so it turns out this guy is a little brown species. So you can tell this when you add this in that iodine did mix down with this layer, because this layer becomes very brown, reddish brown. Whereas this layer will be still clear, meaning the iodine was dissolved in this layer. Okay, so let's try that idea one more time. This time though, again the 2 water and CCl4 layer, we add nickel nitrate. Nickel nitrate is a green substance. So, and these 2 are clear. I didn't mention that before, but these 2 are clear, and colorless solutions or substance, liquids. Where do you think the green layer will be? Will the green go into the water layer, or the green nickel nitrate go into the CCl4 layer? So how would you answer this, right? You look at this and you ask yourself, is it a polar molecule or a non-polar molecule? It's not. It's not a molecule. What is it? It's an ionic compound. If it's an ionic compound, it's positive and negative, cation and anion. So it is charged. If it's charged, which one would it go into? Which one is happy to interact with it? Right? If it's charged, it wants to interact with the water. The water can solvate ionic charges. So it turns out that this dissolves in water and makes that water all green and leaving this clear and colorless. Okay, so the concept there is called like dissolves like. That's a rule that you can apply. Meaning that if you are a polar molecule, you will dissolve something that is polar or ionic. And if you are a non-polar molecule, you will dissolve something that is non-polar. Like dissolves like. So let's do a checkpoint now. The checkpoint reads, which of the following substance will be more soluble in a non-polar solvent? So if it's non-polar solvent and you want it to be solvated in that solvent, that molecule must be polar or non-polar? Must be non-polar, right? So our options here is ethanol,
lithium chloride, sodium sulfate, and C5H12, which is called
pentane. So how would you analyze this without really knowing other information? Remember, we want to look for a non-polar molecule, right? So let's kick out some obvious choices. Number one obvious choice is ionic. Which one of these are ionic? Lithium chloride, that's ionic, right? So if it's ionic, it wants to be dissolved in a polar solvent, not non-polar. Another one that's ionic is sodium sulfate. So both of these are knocked out already. You have two left, ethanol and pentane. Okay, so if you want to look up what ethanol is, and I think I gave you a structure for ethanol in the previous slides. Ethanol looks like this.
carbon, oxygen, hydrogen.
Ooh, you see that there's that oxygen right there? That oxygen, and because it is 2 atoms connected with 2 lone pairs, this is a bent shape. What does that look like to you? Kind of like water, right? So you can prove yourself that if this is a bent shape and it has a polarity in its bond, then it will be a polar molecule. So ethanol is in fact a polar molecule. Why don't you try to prove to yourself that it is a polar molecule? But regardless, because it is a polar molecule, it will not dissolve in a non-polar solvent. So our answer is D. And how are we sure it's D? It's a molecule that only has carbon and hydrogen. No matter how those things are connected to each other, if it's only carbon and hydrogen, those bonds are going to be non-polar. So this is your answer. Non-polar dissolves in non-polar solvent.